Showbiz and Shotties. Welcome to the Organ System Integration Part 1 of the Special Senses module. So the special senses help us interpret the world, and this includes smell, hearing and balance, vision, taste, as opposed to the somatic sense of touch. So let's start with vision. Our eyes have three concentric layers. You have the external layer, which is the cornea. It actually has a transparent tissue which refracts the incoming light, and also it functions to protect the anterior surface of the eye. The rest of it continues to the back of the eye as a sclera, which supports the shape of the eye. Next, you have the middle layer, which includes the iris. So the iris controls the pupil diameter and limits the amount of light that enters the eye para hindi masilawan. The ciliary body includes suspensory ligaments attached to the lens, which change lens shape for far and near vision. And finally, it continues the back of the eye as the choroid, which is a highly vascularized tissue that nourishes the retina. Then you have here the internal layer, which includes the retina. The retina has this inner sensory layer, which extends axons as the optic nerve. As you can see, the axons of the optic nerve, they travel through the brain to communicate the magic of vision to the visual cortex. But let's take it one step at a time. First, what is the retina? So our retina has 10 different layers. Let's orient ourselves with that. The top is actually the innermost part of the eye, and the bottom is what lies on the choroid or the vascularized region. So the pigment epithelium is the most external layer of the retina abutting the choroid. It contains melanin, which absorbs light and decreases light scatter in the eye. Doon nakaupo yung rods and cones. The outer limiting membrane naman is a layer separating the cell material of the photoreceptors from their nuclei. So here puro nuclei lang yan. The outer nuclear layer contains the nuclei of rods and cones. Then the outer plexiform layer contains the rods and cones axons. So this includes mga horizontal cell dendrites, bipolar cell dendrites. The synapses occur here. Then you have the inner nuclear layer, which has nuclei of the second order neurons or the supporting Mueller cells. And you have the inner plexiform layer, which contains the synapses between the dendrites of ganglion cells and amacrine cells and the axons of the bipolar cells. And finally, you have here the ganglion layer, which contains the nuclei of the ganglion cells, whose axons become the optic nerve fibers itself, and on top of which is the inner limiting membrane, which is the basal lamina acting as a boundary between the retina and the vitreous body. So this is the mnemonic we have to try and memorize the layers of the eye. So starting from the inner area of the eye to the outer. In new generation, it is only ophthalmologist examines patient's retina. So let's talk about photoreception in the rods. How does the retina detect light and send signals? So it does it through the photoreception process in the rods and the cones. So the first step is when light on the retina will convert the 11 cis-rhodopsin to an all-trans-rhodopsin in the process called photoisomerization. A series of intermediates is then formed, one of which is meta-rhodopsin 2. Now the meta-rhodopsin 2 activates a G protein called transducin, which in turn activates a phosphodiesterase. So the phosphodiesterase is an enzyme that breaks up the cGMP, so cGMP levels will decrease, and the decreased levels of cGMP will cause closure of the sodium channels, a decreased inward sodium current, and as a result, hyperpolarization of the receptor cell membrane, and increasing light intensity increases the degree of hyperpolarization. So when the receptor cell is hyperpolarized, there is decreased release of neurotransmitter, and that's how the signal is sent to the rest of the optic pathway. So let's talk about the optic pathway. In the optic pathway, you have axons of the ganglion cells forming the optic nerve and the optic tract that end in the lateral geniculate body of the thalamus. Then fibers from each nasal hemiretina cross at the optic chiasm, whereas the fibers from each temporal hemiretina remain ipsilateral. Therefore, fibers from the left nasal hemiretina and fibers from the right temporal hemiretina, they form the right optic tract. And they synapse on the right lateral geniculate body. And then fibers from the lateral geniculate body form the geniculocalcarine tract, and they pass to the occipital lobe in the cortex. So, cutting the optic nerve will cause blindness in the ipsilateral eye. So you can see here na if blind yung kanyang isang eye, there's only vision in the whole other eye. Now, cutting the optic chiasm naman will cause heteronymous bitemporal hemianopia. So cutting here in the middle will cause destruction or loss of fibers receiving from the temporal fields. And cutting the optic tract itself will cause homonymous contralateral hemianopia. And finally, cutting the geniculocalcarine tract will cause homonymous hemianopia, but with macular sparing. And that was vision. So we have a phrase here. Seeker tells us to open our eyes as wide as the stars. Let's move on to hearing. Let's talk about the ears. Now, the ear mediates both hearing and equilibrium. The ear contains of three major parts. The external ear, which receives sound waves. The middle ear in which sound waves are transmitted from the air to the fluids of the internal ear through a set of small bones. And finally, the inner ear. This contains the cochlea, in which the fluid movements are transduced to nerve impulses that pass via the acoustic nerve to the CNS. The internal ear also contains the vestibular organ, which allows the body to maintain equilibrium or balance. Note that the structures of the middle and the inner ear form the head mesenchyme, and they become enclosed within the temporal bone. So these delicate structures are actually protected by the temporal bone and closely associated with the rest of the brain. So with that, we have the auricle or the pinna. So this is an irregular funnel-shaped plate of elastic cartilage, and it is the shape because it directs sound waves into the ear. Then you have the external acoustic meatus, which is a canal from the auricle to the middle ear, and it's lined with stratified squamous epithelium. So this is a section of the external meatus near the opening, which shows skin, and this skin is rich in hair follicles. You see a lot of hair follicles here, hair follicles, sebaceous glands, or oil glands, and ceruminous glands. So ceruminous glands are special glands that produce cerumen, earwax, or the tutule, which is a waxy material with the protective antimicrobial properties. Now, this wall is supported by elastic cartilage in its outer third, and the inner part is enclosed by the temporal bone. This canal leads to a thin membrane called the tympanic membrane or eardrum. This is a fibroelastic connective tissue. Outside, it's covered with epidermis, but internally, it's covered by the simple cuboidal epithelium of the mucosa that lines the middle ear cavity. So the sound waves here from the air will cause vibrations of the tympanic membrane, and this transmits energy to the middle ear by moving a set of bones. So the middle ear will contain the air-filled tympanic cavity within the temporal bone. And between the tympanic membrane and the bony surface of the internal ear, you have this chamber. So anteriorly, the space will extend as an auditory tube or the eustachian pharyngotympanic tube to the pharynx, while posteriorly it communicates with the mastoid cavities of the temporal bone. So the relevance of the pharyngotympanic tube or the eustachian tube, well, below the tube is usually collapsed, and then swallowing will actually open it briefly, and that serves to balance the air pressure in the middle ear with the atmospheric pressure. So in the medial wall of the middle ear, there are two small windows, the oval and the round window, within the inner ear behind them. The tympanic membrane is connected to the membrane of the window by means of the three small bones. You have here the auditory ossicles. They transmit the mechanical vibrations of the tympanic membrane to the internal ear. And you have here, aside from here, you have here two small skeletal muscles, the tensor tympani. Then you have also stapedius, which insert into the malleus and stapes, and they are thought to function to limit the ossicle movements and limit sound transmission. So the internal ear is located completely within the temporal bone, and the cavity in the temporal bone is the bony labyrinth, which houses a fluid-filled chamber and tube called the membranous labyrinth. So the cochlear duct within the cochlea is a spiral organ that detects the sounds being transmitted from the middle ear. So continuous to it are the two continuous sacs called the utricle and the saccule. They detect the linear movements and the static position of the head. Then you have three semicircular ducts are connected, which detect the rotational movements of the head. So let's talk about cochlear duct and hearing. So the cochlear duct is actually a spiral tube encased in a spiral-shaped bony cochlea. So yeah, spiral shape. So taking a cross-section of the tube, the cochlear duct itself forms the middle compartment, filled with endolymph called the scala media. The endolymph, okay, why is it important? It's potassium-rich fluid. It's produced by the stria vascularis. Now outside the tube, the surrounding lymph that runs here is called perilymph, and the compartment above it is the scala vestibuli, which is separated by a very thin vestibular or Reisner's membrane. And the compartment below it naman is the scala tympani, which is separated by the basilar membrane. So let's try to focus a bit more on that area. Lying on the basilar membrane is this thing called the organ of Corti, where sound is detected. It consists of special sensory hair cells with protruding stereocilia. So you have the hair cell, and then you have the protruding stereocilia. The tops of the stereocilia are embedded in a gel-like pectoral membrane. So when the embedded stereocilia move, the hair cells act like mechanical transducers that transmit the movement as signals to the nerve. So how does this mediate hearing? As we saw, the sound waves are collected by the external ear, and they hit the eardrums. They cause the tympanic membrane to vibrate, and then this moves the chain of middle ear ossicles, and it hits the oval window. So the oval window is adjacent to the scala vestibuli compartment, and the vibrations are carried by the liquid perilymph, moving along the perilymph compartment. And as the vibrations move, they can momentarily displace the basilar membrane. And then lying on the basilar membrane, kasi is this organ of Corti, and then where displacement of the basilar cells will cause displacement of the sensitive hair cells in the organ of Corti, and this initiates a nerve signal in the cochlear branch of cranial nerve 8. So you can think of the cochlear ducts as a spiral piano in which the organ of Corti or the key is pressed. and it depends on the frequency of the sound wave being transmitted. So, mga high freq sound waves will displace near the base of the cochlea, while low freq sound waves will displace near the apex of the cochlea. And this is how our brain can interpret the different neuronal signals as a world of sound. So, for those who watched Your Lie in April, it is said that by exchanging notes, you get to know one another, to understand one another, as if your souls were connected and your hearts were overlapping. It's a conversation through instruments, a miracle that creates harmony, and in that moment, music transcends words. So that was hearing, guys. Now let's move on to the vestibular complex and balance. So how does the uticle and saccule detect linear movements and the static position of the head? You know, the walls of the uticle and saccule, they each have a second area called the macula. So it's the macula. The macula contains, again, sensory hair cells, and they have connections to the nerves. So projecting from each hair cell are many sericilla and one kinocilium. This is all embedded in a gelatinous matrix which has otolith crystals. So when you have head movements, they will cause the otolith and the gel-like substance to move. And this will cause movement of the cilia on the hair cells, which are sensitive, and they cause the polarization and sending of the nerve impulses. And in this way, you can detect the linear acceleration or position of the head. Now, how do the semicircular ducts detect the rotational movement of the head? So each of the semicircular ducts are oriented 90 degrees from one another. Okay? And each duct, it has a terminal ampular region here, called the crista ampularis, which contains hair cells embedded in a gel-like cupola. So the head movement displays the endolymph. For instance, if you look to the left, the endolymph in the right horizontal canal by spaces will move the opposite way. So parang ganun. Yeah. The endolymph movement will displace the cupula, which moves the embedded spherocylia, and the sensitive hair cells will produce signals to contribute to the sense of equilibrium. So how does the movement of the spherocylia in each hair cell lead to transmission of the nerve impulses? So we'll be looking closely at the example of the hair cells in the macula of the uticle and saccule. At rest, the hair cells are polarized with a small amount of potassium entry and a low level of neurotransmitter release. Head movements that cause the spherocylia to be directed towards the kinocilium will produce tension in the tip links, which produce adjacent cation channels. Nag-open yung adjacent cation channels. So the entry of the potassium will depolarize the cell and lead to opening of the voltage gated basolateral calcium channels, yeah, potassium calcium, and cause the release of the neurotransmitter. Now, the movement in the opposite direction or away from the kinocilium will produce slacking of the tip links, closing of the channels, and hyperpolarization, and thus it inhibits neurotransmitter release. And that was balance. Let's move on to smell. So we have two nasal cavities, yeah, the left and the right, and they're separated in the middle by the nasal septum, which has the osseous component, and the rest is actually cartilaginous. So let's enter each cavity. The left and right nasal cavity each has a dilated vestibule, which leads to the internal nasal cavity. From the nostril to the vestibule, there are rich vibrissae that filter out the large particles from the inspired air, and the lateral walls has three bony shelf-like projections. So imagine my bookshelves in the lateral side. They are called conchae or the turbinates. So the conchae or the turbinates, they have mucosa covering them. They have a complex vasculature that carries blood counter to the flow of inspired air to warm and humidify the air being inhaled. And it's covered with mucus and glands that further trap and remove more impurities from the air. The nasal secretions also have an additional protective immunoglobulin E. So let's try to take a section of the roof of the nasal cavities. The superior conchae, because this component is actually covered with specialized olfactory epithelium. While the rest, the middle and inferior conch, are covered with respiratory epithelium. So, respiratory epithelium, right on the basement membrane, on which are small rounded basal cells. These are the stem cells. Then you have the middle-sized cells. Then you have the tall, columnar cells with cilia. So these are also called goblet cells, which secrete mucus. The mucus films, they trap airborne dust particles and microorganisms. And then they have the ciliary movements naman. They continuously propel the sheet of mucus towards the pharynx for elimination. So the olfactory epithelium. The chemoreceptors for the sense of smell are located in the olfactory epithelium. This is a specialized mucous membrane covering the roof, the nasal cavity, and the superior conch. It also has pseudostratified epithelium, and it contains basal stem cells, columnar support cells, in addition to the bipolar olfactory neurons. So the epithelium has three major cell types. You have olfactory neurons, which are bipolar, meaning that they have an apical pole, which is the dendrite end, and it carries a knob-like swelling from which emerge long hairs that carry the chemoreceptors. So chemoreceptors, they respond to odoriferous substances by generating an action potential, and that is what is carried along the axon. So many axons will unite in the lamina propria as very small nerves that then pass to the brain through the foramina in the cribriform plate of the ethmoid bone, and they form here the olfactory nerve, cranial nerve 1, and eventually they synapse with other neurons in the olfactory bulb. So the supporting cells are columnar. Yan. So they have more apical nuclei and narrower bases. On their free surface, there are microvilli submerged in a fluid layer. And they express abundant ion channels that help maintain a microenvironment conducive to olfactory function and survival. On the other hand, you have basal cells. These are small spherical or cone-shaped cells near the basal lamina. So these are the stem cells for the other two types, which replace olfactory neurons every 2 to 3 months and supporting cells less frequently. So let's take a histopath specimen. And you see here that lying on the basement membrane, this is the basement membrane, you have the basal cells. The nuclei of the bipolar olfactory neurons will lie in the middle of the pseudostratified olfactory epithelium. Yung mga supporting cells, they're the ones with nuclei near the top. And at the apical ends of the cells are the non-motile cilia, or olfactory hairs and a layer of mucus. So how does smell work? The Nobel Prize for Physiology has gone to the scientists who discovered how smell works. So in this process, air carries around lots of aromas into the nasal cavity. And we said there are tons of membrane receptors in the knob-like swellings of the dendrite ends of the olfactory neurons. So each receptor can detect a limited number of substances. Once the odorant binds to the receptor, the olfactory receptor cells are activated by a GPCR way of signal transduction. The similar type of receptors will join together in the glomeruli, and any stimulated receptor cell will send electric signals to the glomeruli. Now, the micro cells, they send signals from one type of glomerulus to a defined region in the brain cortex. So, how's this process? It was likened to each pathway lighting up an LED light, and then the combination and pattern of lit up LED lights is what we interpret as smell. So, the brain can recognize 10,000 different odors, a combination of different signals that evoke scent. So, it is said by Helen Keller that smell is a potent wizard that transports you across thousands of miles and all the years you have lived. So, odors take a direct route to the limbic system, including the amygdala and the hippocampus, the regions related to emotion and memory. And that's why scent, emotion, and memory are carefully intertwined. Now let's move on to taste. So the tongue is a huge piece of muscle. The muscle fibers are oriented in all directions. They allow a great deal of mobility for mastication and swallowing. Now the dorsal surface of the tongue is quite irregular, with hundreds of protruding papillae. The anterior two-thirds of the tongue have various types of papillae. Separating them from the posterior third naman is this V-shaped groove called the sulcus terminalis. So posterior third on the root of the tongue has lingual tonsils. Now let's talk about the papillae. They are elevated mucous membranes that have special function and therefore general types. Yeah, the filiform papillae, these are very numerous. They have elongated conical shapes and they're heavily keratinized. They provide a rough surface that facilitates movement of food during chewing. Then you have the fungiform papillae. These are less numerous. They're only lightly keratinized and they're interspersed among the filiform papillae. This is more mushroom shaped with a well vascularized core of lamina propria with taste buds. Then you have the foliate papillae. The foliate papillae exist on the parallel ridges on each side of the tongue, anterior to the sulcus terminalis. These also have taste buds, but they're rudimentary in humans, especially in older individuals. Then you have the valate or circumvalate papillae, which is the largest papillae. There are like 8 to 12 of them, aligned in front of the sulcus terminalis. Okay? So on histopath, it looks like this, showing pointy filiform and the more mushroom-shaped fungiform papillae. Both have stratified squamous epithelium. And you have a single very large valate papillae with many taste buds, maraming taste buds, around the sides and several small salivary glands emptying into the cleft or the moat. So this is the cleft. So let's talk about the taste buds. Mayoral taste buds on the valate papillae, fungiform, and foliate papillae, and they're also scattered over the dorsal and lateral surface of the tongue itself. So these taste buds, they sample the general chemical composition of the food we eat. You have elongated gustatory or taste cells that live for about a week. Then you have the slender supportive cells, and you have the slowly dividing basal stem cells that give rise to the older cell types. The base of each taste bud, it rests on the basal lamina and it's entered by the afferent sensory axons that form synapses with the gustatory cells. So at the apical instrument of the gustatory cells, you have the projection of microvilli towards the taste pore, and the microvilli has taste receptors for detecting taste buds. So the taste buds detect at least 5 broad categories of taste buds. The salt and sour tastes are produced by ion channels, and the other 3 taste categories are mediated by G protein coupled receptors. The receptor binding produces the polarization of the gustatory cells, stimulating the sensory nerve fibers that send information to the brain for processing. And it said that good food is the foundation of genuine happiness. So that, my friends, was an overview of the special senses, and I'll see you on Module 2 to talk about the pathologies.